Okay, this video is on Newton's universal law of gravity. So the story goes that Newton was sitting under an apple tree and an apple fell on his head and he magically came up with his law. Now, that probably didn't really happen, but the genius of Newton was that he was able to realize that the force that pulls the apple down towards the Earth is the same force that keeps the moon in orbit around the Earth. Right? So he was able to expand gravity from just an earthly force, a force that happens near the surface of the Earth, to a universal force, a force that expands throughout the universe. And through some mathematics, he was able to come up with an equation. So he said that the force of gravity is equal to a constant called g, uppercase G, and the two objects, m1 and m2, and the distance between those objects. So r here is the separation between the masses. Okay, and it's important to note that it's from center of mass to center of mass. So m1 and m2 could be any two masses in the universe. So the Earth and the Moon, the Earth and the Sun, me and the Earth, me and this pen, they all have a force, a gravitational attraction to each other. Okay, so this force of gravity is always an attractive force. And this other constant here, g, is the universal gravitation constant. You can look it up on your formula sheet. It's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Okay, and it's the universal gravitation constant. Okay, so this equation tells us the force of gravity, the gravitational attractive force between any two masses in the universe, as long as we know the distance between these masses. And again, it has to be from center of mass to center of mass. Okay, so the other thing that's important is that force, the force of gravity, the gravitational attraction, appears or acts on both masses. So if this is the Earth and the Moon, they both experience the same magnitude of force, just in opposite directions. Okay? So even though the Earth is pulling downwards on me, I am also exerting a force upwards on the Earth. It's an equal but opposite force, right? Basically Newton's third law. Now, the only difference is the direction of the force, right? The Earth pulls downwards on me, I pull upwards on the Earth. Now the Earth is so massive that it doesn't really accelerate based on the tiny amount of force that I'm exerting on it. But relative to me, it's a large force pulling me downwards. The other thing to note about this equation or this relationship is that if we plot the force of gravity on the y-axis and the separation r on the x-axis, as r increases, what we find is that the force is proportional to 1 over r squared. Okay, this little Greek symbol here, alpha, we use that for proportional, which means that this is the relationship between F and R. So as as R increases, so if R was to go, say, from 2 meters to 4 meters, I would go from 1 over 2 squared, so a quarter, to 1 over 4 squared, a 16th. Right? So it's a 1 over r squared relationship, and that looks like this. So as r increases, F approaches 0, never quite get to 0, but we have this exponential decreasing graph, and we have a 1 over r squared. Well, we often call that an inverse square relationship. And this type of relationship appears a few times in physics, which is why we refer to it quite often. It's an inverse square relationship, or inverse squared relationship. So as the distance between the objects increases, the force decreases with the square of that distance. Okay, so basically now we have two different ways of calculating the force of gravity. The first way is if we know the acceleration due to gravity, which is our lowercase g, right? That's the acceleration due to gravity. We also have another equation now, which is Newton's universal law of gravitation. Now these two equations should be equivalent to each other. They both tell me the same force. So for example, say I was trying to calculate the force of gravity on me standing on the surface of the Earth. Using this equation, I could put in my mass, and I'm just going to say I weigh 100 kilograms to make the math a little bit easy. And I multiply that by the acceleration due to gravity. It's a negative acceleration, so I get a direction for this force. It's negative 980 newtons, right? So I'm pulled down with a force of 980 newtons. If I use Newton's universal equation, I get the same answer, right? I put in my constant. I'm going to leave the units out of this side. M1 is my mass. M2 is the mass of the Earth. And again, you can look this up on your formula sheet. It's one of the constants that you're given. 5.98 times 10 to the 24 kilograms is the mass of the Earth. And then I divide that by the square of the distance. Now again, it's the distance between me, the center of mass of me, and the center of mass of the Earth, which for all intents and purposes is just the radius of the Earth. And again, you can look up the radius of the Earth, 6.38 times 10 to the 6 meters from your formula sheet. And don't forget to square that number. And what you find is that you get the same force, 980 newtons. Okay? So these two equations are equivalent to each other. We get the same value. Okay? Keep in mind, again, that this is from center of mass to center of mass when you're looking at the separation. The only difference between these two is obviously the direction. This one is a universal force, so it comes out as a positive number, meaning that it's the force that I exert on the Earth. It's also the force that the Earth exerts on me, so it doesn't include the direction. We know that it's a mutually attractive force. Here, because I'm given the acceleration as negative, I end up with a negative answer because I'm definitely finding the force on a 100 kilogram mass. The force on me is definitely downwards. This one tells me the force on both masses, and they're equivalent to each other but in opposite directions. Okay, the other thing that's useful about these two equations is I can set them equal to each other. So mg equals g m1 m2 over r squared. This mass m1 cancels, and what I have now is an equation which tells me the strength of the gravitational field. So rather than calling this the acceleration due to gravity, we could also call this the gravitational field strength. So this is the gravitational field of mass 2, the mass that's at the center of the circle, a distance r from that circle. So I can now find the gravitational field strength, or the acceleration due to gravity, at any distance from the Earth. And I can do the same thing for any distance from the sun or any distance from the moon, whatever object I'm interested in. I can now tell what the gravitational field strength is. If we look at the units here, I have uppercase G, our constant, which is in Newton meters squared per kilograms squared. And then I have kilograms for M2. So one of those cancels. And then I'm dividing by meters squared. So that cancels. And what I'm left with for the units for gravitational field are newtons per kilogram. Okay, so G could be an acceleration in meters per second squared. It can also be the gravitational field strength, which is how many newtons of force are acting on every kilogram of mass at that point. Okay, so again, given a distance from the Earth, I can plug those numbers in and tell you what the gravitational field strength or the acceleration due to gravity is at that point. Okay, in the next video we'll take a look at gravitational potential energy in a slightly different way than we looked at it in a previous unit. Okay?